In this lesson, I am going to discuss orthogonal vectors in Rn. Two vectors u and v are said to be orthogonal or perpendicular if the dot product between u and v is equal to 0. We have seen this in our last video lecture. The next theorem tells us a sufficient and necessary condition for two vectors to be orthogonal. Two vectors are going to be orthogonal if and only if they satisfy the Pythagorean theorem. That is, the magnitude of u plus v squared is equal to the square of the magnitude of u plus the square of the magnitude of v. So here is a picture of two orthogonal vectors, u and v, and the length of the sum of the two vectors. This one will be equal to this, the norm of u squared plus the norm of v squared. Let us find orthogonal vectors. Suppose that we want to find all the vectors in R2 that are orthogonal to 4, 2. This means that we are looking for vectors v of the form AB such that u dot v is equal to 0. So we have 4, 2 dot AB is equal to 0. This means that 4a plus 2b is equal to 0, which means that a is equal to negative 2b over 4 or negative b over 2. So hence, we can let b to be any real number. So our v is of this form, negative b over 2b, where b is any real number. This is equal to b times negative 1/2, 1. So hence, the span of negative 1/2, 1 is the set of all vectors that is orthogonal to the vector 4, 2. Next, we are now in R3. We also want to find all the vectors that are orthogonal to this u here. So let us call that v x1, x2, x3, and we want u dot v to be equal to 0. So we have 1, 1, negative 1 dot v, which is x1, x2, x3 is equal to 0. This dot product is equal to x1 plus x2 minus x3. Take note that we have 3 unknowns, but we only have one linear equation. That means that we have 2 free variables. So I can let my x1 and x2 to be free variables. And x3 is just equal to the sum of x1 plus x2. So hence, my v is of this form. Let me call x1 r and x2 s, because they are free. So x1 is r, x2 is s, and x3 is r plus s. This is the set of all vectors that is orthogonal to our vector u. Let us find a spanning set for this. To do that, we will collect all the variables r. We will separate them with s. Therefore, this is r times 1, 0, 1 plus s times 0, 1, 1. Hence, this set is the span of these two vectors, 1, 0, 1 and 0, 1, 1. For the next example, we want to find all vectors orthogonal to both u and v. What we want to do is to find all w's such that u dot w is equal to 0 and v dot w is equal to 0. Let me call my w x1, x2, x3. U dot w is equal to x1 plus x2 minus x3. We want that to be equal to 0, and v dot w is equal to x1 plus x2 plus x3 is equal to 0. This one will yield this augmented matrix. Notice here that the rows of your augmented matrix, look at this, 1, 1, negative 1, 1, 1, negative 1, 1, 1, 1, 1, 1, 1. The rows of your augmented matrix are just the transpose of U and V. We will see later that in general, this is always the case. When we reduce it to its row echelon form, we will get 1, 1, 0, 0, 0, 1. And therefore, we have a non-pivot at the second column. So that means x2 is a free variable. Let's call it r. And x1 is equal to negative x2, negative r, and x3 is equal to 0. Hence, our w is of this form, negative r, r, 0. If we put this in a set, this is the span of negative 1, 1, 0. Let us now discuss orthogonal complement. Suppose that W is a subspace of Rn. Its orthogonal complement is the subspace of all vectors in Rn that are orthogonal to the vectors in W. So here is a picture of the orthogonal complement of a line in R2. What will be a line in R2? W will be the span of a single vector. Its orthogonal complement will be a line perpendicular to your W. Here I have my V. I can move my V here. V is the blue arrow and purple line is the span of V. Let's call it W. W is the purple line and W perp is the red line. What about if we are in R3? Again, W here is a line, so therefore it is just the span of a single vector. Its orthogonal complement would be a plane. So for example here, the blue line is again my V and the purple line is my W, the span of V. If I move my V here, this plane here is the orthogonal complement of W. What if this time I get the orthogonal complement of a plane in R3? Take note that if you are a plane in R3, you are the span of two vectors, U and V. What is this saying? Its orthogonal complement would now be a line. So here I have my sets V and W. I can move the heads for V and W. The purple plane is the span of V and W, and the red line is the orthogonal complement of this plane. Here are some facts about W perp. Number 1, I have already mentioned that W perp is a subspace of Rn. Next, the orthogonal complement of the orthogonal complement of W is W. And lastly, since W and W perp are both subspaces, we can talk about their dimension, and it turns out that the sum of their dimensions is equal to n. Now, how do we compute for the orthogonal complements? Here's the thing. If S is a set of vectors in Rn, a vector that is orthogonal to S is also orthogonal to the span of the entire S. So that is, the orthogonal complement of S is the same as the orthogonal complement of the span of S. Let me break this down for you. Suppose that we have a set of vectors v1 up to vn, and we are looking for the orthogonal complement of S. S perp. S perp is the set of vectors that are orthogonal to all the vectors in S, correct? This is saying that the orthogonal complement of S will also be the orthogonal complement of the span of S. This is saying that if you are given a subspace W. Of course, if W is a subspace, W can be written as the span of a set of vectors, correct? To get the orthogonal complement of W perp, all you have to do is to get the orthogonal complement of the elements that span it. So let me illustrate that by an example. So notice here that we want to find all vectors orthogonal to W, and W is the span of these two vectors here. We already computed for the set of vectors orthogonal to both U and V, and we saw that it's equal to span of -1, 1, 0. Since this set is orthogonal to these two vectors here, it will also be perpendicular to all the elements in the span. So this one will also be equal to W perp. So to continue with our discussion, we have to discuss null space. Let A be an n by n matrix. The solution set of Ax equals 0 forms a subspace of Rn, and this is called the null space of A. Why are we interested with the null space of a matrix? Suppose that we have a set of vectors in Rn, and let W be equal to the span of these vectors. Let A be the matrix whose columns are the elements of S. Hence, your A is V1, V2 up to Vn. Remember that V1, V2 up to Vn are column vectors, correct? Because they are vectors in Rn. If we want to get the orthogonal complement of the span of this, it will be equal to the null space of A transpose. Let me illustrate that. Suppose that this will be our U, V, and W, and we want to find W perp, where W is the span of U, V, and W. According to our theorem, to get W perp, we just have to get the set of vectors that are orthogonal to U, V, and W. Let us now find the set of vectors perpendicular to U, V, and W. Let us call my vector x. This is x1, x2, x3. U dot x is equal to 0. V dot x is equal to 0. And W dot x has to be equal to 0 as well. I will do first the long method, and then I will show you how the theorem works, so that you will really see that W perp is equal to the null space of A transpose. We will form our A later. So let us look at U dot x. So U dot x means that x1 plus x2 plus 2x3 is equal to 0. For V dot x equals 0, we have x1 minus x2 plus 2x3 equals 0 because V is this. For W dot x to be equal to 0, we have 2x1 plus x1 minus x3. This one is equal to 0. Let us transform this into its augmented form. This is 1, 1, 2. This is 1, negative 1, 2, 2, 1, negative 1. I will show you now where the A came from. From our theorem, how do you form your A? Your A is the matrix whose columns are exactly your column vectors. 1, 1, 2, 1, negative 1, 2, 2, 1, negative 1. And what can you observe, class? This is now your A transpose, right? So when you were solving for X here, you have to solve this system. Since this is A transpose, you are getting the solution of A transpose X equals 0, correct? And when you are solving for this set X, that is the same as looking for the null space of A transpose. So from now on, the shortcut is this. transforming the vectors, the column vectors into rows. Look at this, 1, 1, 2, 1, 1, 2, 1, negative 1, 2, 2, 1, negative 1, and solving for this system. When you convert this to its reduced row echelon form, you will get the identity matrix. So that means that x1, x2, x3 is equal to the 0 vector. So hence, in this case, our W perp is equal to the 0 vector. And why is that? Take note that U, V, and W are linearly independent and they consist of 3 vectors. W is actually the entire R3. Hence, the set of vectors which is perpendicular to all the vectors in R3 is just the 0 vector. Next, let us discuss the orthogonal projection. Let U and V be vectors in Rn with V a non-zero vector. The orthogonal projection of U onto V is this vector. You have the dot product of V over the length of V squared times V. I suppose that this is my V, non-zero, and this is my U. When I project U onto the vector V, and it says orthogonal projection, what will happen is that I will get this part here. So I want this line segment to be perpendicular to V, and this vector here, this black vector, is now your projection of U onto V. Let us dissect this part here. Notice that we can write this as U dot V over the norm of V, V over the norm of V. This is the unit vector in the same direction as V. And therefore, what is the length of this vector? This is just a scalar. So a scalar times a unit vector, what will be the length? It's equal to this scalar here, correct? So hence, if we look at our diagram here, the length of the projection of U onto V is equal to the dot product of U and V over the norm of V. And this one here, the V over the norm of V, it gives us the direction. So for example, let us find the projection of U along V, where U is 2, negative 1, 3, and V is 4, negative 1, 2. Let me write down the formula first. U dot V first is 2 times 4 plus negative 1 times negative 1 plus 3 times 2. This is equal to 8 plus 1, 9 plus 6, that's 15. Next, the norm of V squared. We just get the square of the components. We do not need the square root anymore because it will be cancelled by the square. So that's 4 squared plus negative 1 squared plus 2 squared. So that's 16 plus 1, 17 plus 4, 21. And therefore, the projection of U along V is U dot V is 15 all over 21 times the vector V. 15 over 21 is 5 over 7 times V, 4, negative 1. You can leave it as that, or you can also write it as 20 over 7, negative 5 over 7, 10 over 7. We are now ready for our next theorem, the projection theorem. Suppose again that we have two vectors in Rn, U and V, with V not equal to the 0 vector. Then we can express U in exactly one way in the form U equals V1 plus V2, where V1 is a scalar multiple of V and V2 is orthogonal to V. Suppose these are my vectors U and V. This theorem is saying that we can write U as a sum of two vectors where one vector is parallel to V, or it's in the direction of V, and the other vector is orthogonal to V. Let me first draw a vector which is orthogonal to V. let's say that one, what would be my V1 and V2? So in order to do that, I will first get the projection of U onto V. So this vector here, this is my V1. And when I project U onto this vector, which is orthogonal to V, this is now my V2. How do we get this V1 and V2? Notice that V1 is just the projection of U onto V. And how do you get V2? You do not need to get this vector orthogonal to V and then project U there. What you just need to do is, from this equation, V2 is just equal to U minus V1. Let's have an example. We still have the same vectors, U and V. Now we want to find the vector component of U along V and the vector component of U orthogonal to V. That is, we want to write U as V1 plus V2, but we already know that V1, this is the projection of U along V. We already calculated that it is equal to this vector. And therefore, V2 is just equal to U minus V1. This is equal to negative 6 over 7, negative 2 over 7, 11 over 7. Let us check our answers. We will now plot our vectors in this 3D calculator. So first, I will plot my point 2, negative 1, 3. I will form a vector A. That's my U. Let me just hide my A there so that only U will appear. For the vector V, I have to plot 4, negative 1, 2, and form a vector with that endpoint. Let me just hide my B there. Let's move in closer. Now let us just verify the orthogonal projection of U onto V that we computed earlier. We have 20 over 7, negative 5 over 7, and 10 over 7. Let us form a vector containing C as the endpoint. There you go. I now have my W here, and it is really parallel to V. And if you look at this, if you form this line segment, it will be orthogonal to your V. Let us now compute our V2. That is just U minus, our V1 here is W. There you go. So as you can notice here, if you form this line, that one, and that one. So these are the vector components of U along V and a vector orthogonal to